Okay, so we've spent some time on each of the component parts of a decision problem, particularly the two-class problem. And I'm hoping that by now, if, for example, I asked you to design a system to classify email for being spam or not spam, you could at least conceptually think about it in terms of, well, you need a way of computing a likelihood ratio for each email being spam or not spam, and then you need some way of quantifying what proportion of emails are spam versus not spams, and then you'd need a cost, which might be different for different people, of course, for making the two types of mistake, that is classifying ham as spam and classifying spam as ham. And once all those components were in place, you would be able to, for any given email, compute a likelihood ratio, combine that with the prior odds to get a posterior odds and a posterior probability, and then compare that posterior probability with the costs to make a decision about whether to make it put it in the inbox or put it in the spam filter. And we kind of touched on the idea that we're choosing the action that minimizes the expected loss or the posterior expected loss there. But so more generally, you might ask, well, why should I do things this way? Or what guarantees can you give me if I do things this way? What guarantees can you give me? And the short answer is that if all the modeling assumptions that go into this procedure are correct, then this whole procedure will minimize your overall average loss in the long term. So that's the short answer. And that the basic framework doesn't only apply to making decisions between two possibilities, it also applies more generally. So a more general point and a kind of summary of what, a more precise statement of the statement I've just made is given in this vignette here. So this last one. Yeah. Okay, so let's go over this briefly. So here we're going to consider a problem that's a bit more general than the classification problem. You can call it a prediction problem. And I'm going to use Y as the thing you want to predict and X as the data that you're using to make your prediction. Okay, so in the email example, Y would be spam or not spam. That's kind of the prediction problem. And X would be data on the email. But Y could also be a continuous outcome. So for example, you could be trying to predict voter turnout in each district based on things that you know about the district. That would be the predictors. X, maybe, what proportion of people are college educated or different socioeconomic indicators in about the district. And you might have a bunch of districts and you want to predict what the voter turnout will be in each district. So Y could be, the point is that Y could be a continuous variable as well. Okay. Or in our elephant example, it was discrete. We wanted to predict Y was discrete. That's savanna or forest, and X was the genetic data. Okay. So, so in this general case, the idea in these prediction problems, the idea is that there's some true value that we want to predict, and the loss is going to basically say, how bad is it if I predict some value Y hat when the true value is Y? Okay. So it's kind of the special case here is that what we're trying to predict and the true value lie in the same kind of space, right? There's some, so, that's not always true, that you could have a decision in general, you could have a decision space that is not the same space. You could be trying to make a binary decision when about a continuous, based on a continuous unknown variable. But in general, in prediction problems or inference problems where we're trying to estimate something, that's another example here, we're going to define, we have an estimate which I'm going to call y hat here, or a prediction. Y hat could be a prediction, could be an estimate. They're different, I guess, but the same framework can be applied in both cases. And so we're going to define a loss function to say how bad is it to predict y hat if the true value is y. And so this comes up commonly enough that there's been some, a lot of work on this, and there's some commonly used loss functions that I want to mention here. So one loss function is simple squared loss. So you just, this might be, if y is continuous, you might just take the difference between your prediction and the true value and square it, and that's how bad it is. Another possible loss function is absolute loss, just the absolute difference between the two values. And then if y is discrete, then it's a simple loss function is just what's called 0-1 loss, which is where you lose 0 if the prediction is correct and 1 if the prediction is incorrect. Right? So of course there are other possible loss functions, but these three kind of generic loss functions are kind of useful to keep in mind as examples. And then to make a formal statement, we need to introduce what we mean by a decision rule. So basically a decision rule now is a way of predicting y from x. So that is, it's a function y hat of x, which for any given x produces a predicted value y hat. Okay. So then here's a key idea, is to define what's called the integrated risk, or also just essentially the expected loss for a particular decision rule. But in order to compute an expectation, you need to say something about what you're computing expectations over, of course. So what you have to think about is applying this decision rule to a series of examples, a series of XY pairs where you're given X and you have to predict Y. And these XY pairs are going to come from some distribution. That's the assumption here. They come from some joint distribution, P of X and Y. So imagine you've got a decision rule and you're going to be applying that decision rule to some samples, some examples, X and Y that are generated from this joint probability distribution. So what's the average loss going to be if we do that? Well, it's just an integral here, or if X and Y are discrete, of course, this integral just becomes a sum. So it's just integrating over the set of examples, P of X given Y here, of the loss, the expected loss, where, so here the idea is that you're thinking about this as a function of y hat. I could give you different decision rules, and we could ask, at least if we knew, in principle, if we knew P of X and what the joint distribution P of X, Y, and if we know the loss function, then we can compute this thing called the risk for any given decision rule y hat. So that's the integrated risk. Okay. So think about the integrated risk as just the average loss you would suffer if you used this particular decision rule y hat over the long run. Okay. And so it's not hard to show that the optimal decision rule is this one here. The optimal decision rule is the one that minimizes what we previously called the posterior expected loss. That is essentially, how do we define y hat op here? We compute, given any given x, we compute the conditional distribution P of Y given x. I mean, to do that, we would need to know what the joint distribution of y and x were, but let's suppose we did know it. So this is kind of a conceptual idea right now, which is nonetheless helpful to keep in mind. So even if we don't know the joint distribution, we might not be able to do this, but the idea is if we knew that joint distribution, this is what would be optimal. It would be to compute this conditional distribution. And then for each possible action, that's what A stands for action here, or in this case, the action is an estimate or a prediction, y hat. So for each possible prediction, A, we compute the expected loss under this conditional distribution. And then we choose the action or the prediction that minimizes that posterior expected loss. So that is this is exactly the kind of rule we talked about last in previous lectures about minimizing the posterior expected loss given data. It's just basically written a different way. The idea again is if I'm going to develop a prediction rule, the optimal one is the one that computes the conditional distribution of y given x, and then computes for each possible prediction the expected loss, and then chooses the prediction that minimizes this. And the proof is straightforward. You can go through it in your own time here in the vignette. So let's see some examples. Actually, interestingly, this is the most important example here, which is that if you use squared loss, so plugging in that squared loss here into the formula, we're trying to minimize this function here, and assuming everything's well behaved and we can differentiate under the integral side, you just differentiate, set its derivative to 0, and you find that the optimal prediction is the conditional expectation of y given x. Okay. So what in a Bayesian context you would call this the posterior mean for y given x. So if we put this into Bayesian language, the optimal predictor under squared loss is the posterior mean. So on the other hand, or if you don't like the Bayesian language, if you prefer just different language, it's the conditional mean. It's the mean of y given x. That's the optimal predictor under squared loss. Actually, it turns out that if you use the absolute loss, it's not as easy to show, but the optimal rule is to set the predictor to the median. So the posterior median, or the conditional median, is optimal under absolute loss. Okay. So you can think about if you're trying to decide, should I summarize my posterior distribution by a mean or a median, you can think, well, the answer kind of depends on what my loss function is. Yeah. So that's one way of thinking about that. If I think the absolute error captures my loss, my utility, my loss better, then I should use a posterior median. If I think the squared loss captures my utility better, I should use the posterior mean. So of course the squared loss tends to really penalize big errors more than the absolute. So all right, well, and then I guess if in the discrete case where you have 0, 1 loss, then the optimal it's the posterior mode that's optimal. So that's kind of nice, is that you can think about choosing the mean, the median, or the mode depending on your depending on your loss function. And actually, this is less of an exercise. It's a useful exercise. It should be fairly straightforward. Okay, so as this section here talks about how the connections between Bayesian inference. So I've been using some of the phrases from Bayesian inference. You don't have to think about this in terms of a Bayesian procedure, though. You just think about applying some decision rule to a sequence of y's and x's that are generated from some distribution, and under squared loss, the optimal predictor for y is its conditional mean, the conditional expectation of y given x, which in a Bayesian context we would just call the posterior mean, thinking of x as data. So, okay, so because of this, the integrated risk is often referred to as the Bayes risk, or the optimal integrated risk is often referred to as the Bayes risk, and the optimal decision rule is often referred to as the Bayesian, or the Bayes decision rule. And that's actually true both in Bayesian decision theory and, if you like, frequentist decision theory. It's kind of like this is kind of like a frequentist optimality of a Bayesian procedure. Why do I call it frequentist? It's frequentist in the sense that it's an on average across repetitions of a procedure. However, it's Bayesian because it's the repetitions are not all under, well, they're not necessarily under a single parameter setting. Okay, if you don't get that, don't worry about that. Just focus on this idea that this procedure where we compute the conditional distribution of y given x, and then make a decision that minimizes the expected loss given that conditional distribution. That procedure is optimal on average if we just draw x and y repeatedly from p of x and y and just apply that decision rule. You can't do better on average in terms of the loss. Okay, so of course, in practice, we might not know this joint distribution. So that's what this theory versus practice. In practice, we might not know what this distribution is. But nonetheless, this kind of optimality could motivate ways of attempting to solve the problem. And so, for example, one way we've already seen, and is the way we've been talking up to now, is that we can specify a prior distribution for y and a likelihood p of x given y. So that's these both came up in the early lectures, and then we use these to compute the posterior distribution of p of y given x. And then all this result shows is that this inference using the posterior will be optimal on average across large numbers of x and y drawn from their joint distribution. So of course, it doesn't guarantee that the procedure will be optimal if you apply it to some set of x and y's drawn from a different distribution. But it's still, it tells you it is what it is. And one way of thinking about this is that the Bayesian inference is optimal on average if both the prior distribution and the likelihood or the model are correct. That's one way of thinking about this, is that that's what Bayesian, one justification for a Bayesian procedure is that if the likelihood is correct and the prior is correct, and you follow the formula of choosing the action that minimizes the posterior expected loss or choosing the prediction that minimizes the posterior expected loss, then you can't do better than that on average. Okay. So of course, most of the debate about whether you should do things this way hinges on the fact that, in practice, we can never know these things exactly. And so of course, there are other ways of doing this, but it's still common to think about comparing methods by looking at their average behavior across a bunch of, for example, simulations, and asking which methods are, on average best, because, that's, if you like, is the only way we can really think about this. Asking about, any given predictor could do well by chance on one go. The idea is what we really want is something that's going to do well on average in the long run.